Hello, welcome back to An Introduction to Audio Programming, a presentation of the 1X Developer Podcast. I'm Brendan,
And I'm Colin.
and this is a segment we call Make Mine a Double Precision Floating Point Value. Let's see. Einstein may have said, if you can't explain it to a 6-year-old, you don't really understand it yourself. Here at the podcast, we say, if you can't explain it after you've had a six-pack, you don't understand it yourself. So that's what we're doing today. We're having a six-pack and explaining audio.
How deep are you into that tonight? That six pack.
I'm on 8. I'm 8
Okay.
into the six-pack.
Wow.
I mean, it's 4:30. What do you?
We have a overflow error, I think.
Yeah, 8 modulo 6.
Yeah.
Let's talk about what audio application frameworks do for us, right? Usually when you're programming audio applications, you want to use some kind of framework, just like any kind of programming. And usually what those frameworks provide is this audio processing callback function. That's the function that we kind of talked about in an earlier video that gets called repeatedly. Every time there's a chunk of samples that's ready to be processed, this function gets called. Audio samples are delivered to the callback function in blocks rather than one sample at a time. And I think, even on modern hardware, it would be a little bit crazy to process one sample at a time just because there is overhead involved in processing every sample. You got to have that thing that we talked about earlier of the audio interface to the operating system to the application, back to the operating system, back to the audio interface. All of that creates a little bit of overhead. And so it would be a little bit crazy to do that one sample at a time, even though in a perfect world, that's how we would do it. We would process one sample at a time. But we do it in blocks of samples. Blocks of samples, which it should be noted, are the number of samples are defined by the user. You can usually define those in your DAW. So
Okay.
The user gets to decide the size of those chunks. And
So, what informs that decision? Why would I say, oh, I want more samples or more block size?
less samples means more responsive but more CPU usage. Larger block size means less responsive but less CPU usage. So if you pretty much want to dial it down to the lowest number that you can that doesn't result in a bunch of clicks and pops. The lowest number you can that your audio plugins can keep up with.
Cool. Okay.
So here's a representation. So far we've been talking about audio that's like sampled of a continuous signal. In the real world, usually, well, I shouldn't say usually, but oftentimes you have like a stereo signal that's made up of multiple channels of audio data, right? So I just wanted to kind of clarify like what we're talking about here. Each individual point here is a sample. Like a sample could be from the left channel, it could be from the right channel. Each individual point is a sample itself. It's often helpful to talk about like all of the samples that are in the same time frame, whatever you call it, right? So that's what we call a frame. And so that would be like the left and the right channel for a given time. And then, left and right channel is just stereo, but there are all kinds of other formats. There are 5.1 and surround and all that kind of stuff. You might have any number of channels, but a frame refers to all of the samples in a given time for all of the samples for all of the channels in a given time.
When we're talking about frames, are we talking on the order of like very, very small fractions of a second?
Yeah. So we had that slide earlier where we were talking about you can derive the sample interval from the sampling frequency,
Mm.
and
Yeah.
so if you have a sampling frequency of like 48,000 hertz, which is not at all wild, um, it was that like point zero zero zero
Yeah.
zero two number. Um, yeah, so
We're in that
samples,
realm of frames. Yeah.
yeah,
Okay.
yep, very 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 small. And then these blocks of samples include they include frames basically. That's kind of why I went that way, right? Sample to frame to block. A block of samples includes all of the samples for a given time range for all of the channels within the audio input.
Mm.
Does that make sense?
Yep.
Yeah. So your audio processing, so given all that, your audio processing callback function will look something like this. It's like you have a two-dimensional float, right? It's a multi-dimensional array of float values. It's an array of channels of samples. Each channel has
Mm.
a certain number of samples, and yeah, right. That's what I'm trying to say. Multi-dimensional array of floats there, and your job is to fill that audio buffer with data. I think one important thing to note, and to be honest, I don't know if this is the case for all audio frameworks, but like at least in Juice, this function doesn't have a return value. Your job is to fill the memory buffer with the correct audio data, and the operating system will come along and like grab that
Okay.
up at the next available opportunity. There's no idea of like returning a value to anything here.
Okay.
It's just you just fill it, and that's as long as you do that on the schedule, life is good.
Okay.
All right. So let's talk about some of these real-time considerations, some of these things that make audio applications responsive. Uh, Garbage collection. You don't want it, pal.
Yeah.
You don't need no garbage collection. This is why C++ is a popular choice. But the basic issue here is that you don't want the garbage collector running in the middle of your audio callback function.
Right.
When you have a function that needs to complete on a schedule, needs to complete in a given amount of time, you don't want the garbage collector running in the middle of that and screwing up your routine. Like, I got a thing going on here. Don't mess with it.
Yeah. And we're talking about like, well, we've already mentioned this in the other videos, like, but this is like we're looking for like super high performance here, right? Like we can't. We, this is one of the programming situations where you really need the super fast thing.
Yes. So yeah, one of the interesting things I think about audio programming, and probably also like video games and stuff like that, it's it needs to be super high performance. It also needs to be predictable.
Hmm.
One of the issues with garbage collection is that like your function might run just fine 9 times out of 10, but then if the garbage collector just happens to run in the middle of your thing, in the middle of your function call, one time out of a million, you drop an audio frame, or you drop an audio, your function doesn't run in
Yeah.
time, or in the case of a video game, your frame gets dropped or whatever. It's super, it needs to be super high performance. It also needs to be really really predictable.
Right.
um, the other big thing is this blocking. You can't have the operating system, you can't do anything that causes the operating system to block. So some really obvious examples of this are like calling out to the network, right? Like in the middle
Hmm.
of your audio callback function, you can't make any calls out to a website, or you can't like write to files or something like that. Those those are maybe more obvious examples of things that could cause the operating system to take an indeterminate amount of time to complete. Um,
I know it's just an example, but I'm like now I'm thinking like would somebody like make an API call based on like you know like hit the network if somebody hits a middle C?
I mean, I think a beginner totally might, right? I maybe it's just me, but like in the beginning, this didn't totally make sense to me. I did not I did not understand. Maybe there's like someone who's like, yeah, every time the user hits a note on the MIDI keyboard, then we call out to some API that translates that into a pitch, and then we generate that pitch or like whatever, right?
Yeah. Okay. I guess. Yeah. And you could do well. I mean, you could make API calls. They just you can't wait for them to respond, right? Just can't block.
Right. So we'll get into that in just a minute, but like basically all audio applications are multi-threaded. This audio callback function is running in its own high priority thread. Um, that's exactly what you said is the key. You can't wait for it to respond. But the big one, and the one that to me was really like not super intuitive, was that you can't allocate memory. Allocating memory is a blocking operation that does not take a uh, cannot be completed within a deterministic amount of time. The operating system
Right. Okay.
can give you back that chunk of memory depending on like what else it has going on, right? um, I that wasn't super intuitive to me when I first started this. I was like, allocating memory, that seems like it's always fast, right? I mean, it is always fast, except like that one time when it's not, and then your audio callback function doesn't complete in time.
Yeah. Yeah.
So
That one is a probably a common gotcha. And printing too.
yeah, when you're debugging, printing to the console is like super, super common. And if you're just debugging, it's whatever. Um, but yeah, if you are actually releasing an audio application, you need to be aware that like any printing to the console is also a blocking operation.
Yeah.
But memory is the big one. Just like everything else in computer programming, memory allocation is like a really really big deal, and it's kind of its own its own kind of thing. So one of the ways that we deal with memory allocation is with a circular buffer. So when the application starts, we allocate a chunk of memory, and we have a pointer to like a write head pointer and a read head pointer, and we kind of like record where we last wrote data, where we last read data, and then when we cycle back to the end, we just start writing over the end, right? We just cycle back to the beginning.
Okay. This is a new idea to me. This is crazy, actually.
It's kind of cool. The basic gist of it is that you allocate everything you need up front, and then you just reuse
Hmm.
that memory over and over and over and over.
I mean, yeah, and it makes sense. Like when you know if you've ever done like assembly on like an 8086 like a VM or something, you only have so many buffers, right? And you have to reuse them.
Mm-hmm.
And in that instance, it's just like, can I release this one? Okay, yeah, it looks like I don't need this one again. I'll write this. But the idea of like this continuous, like, and having like a methodology for where you overwrite, that's cool.
Yeah, it's so in reality, it's kind of this linear. I don't know about in reality, but in our usual abstractions, it's kind of this linear thing. But you can kind of visualize it as a circle, right? You just are going around this circle, and you just are reading and writing over and over in this kind of ring. Hear it called a ring buffer too. Ring buffer, or
Ring
circular
buffer.
buffer.
I think I've heard that actually somewhere. So why the way you have it drawn here, the read pointer and the right pointer are just kind of at different points. Why don't I have my right pointer just in front of my read pointer. So I want to write over the thing I just read, or maybe the other way around. You know what I mean? Like, why wouldn't they be next to each other?
Let's see. Why wouldn't they be next to each other? I think that.
Like, I think, like, just, as someone who hasn't done it and, like, doesn't know anything about what he's talking about, I think, like, if if I'm running out of space, like, if I'm using a whiteboard and I'm writing, right, and then, I'm at the bottom and I'm out of space, I'm going to go back to the top and I'm going to erase that and then write, which is how this works, right? But why not just overwrite? Well, okay, so what is the read pointer actually?
Okay, yeah. So the read pointer is the point at which you are. Let me see if I can. The read pointer is the point at which you are able to consume the data that you've written, right? The write pointer should be ahead of the read pointer. If
Right.
if the read pointer is gets ahead of the write pointer, then you have some kind of overflow, right? Like you have a
Right.
you
Then
have
you're
a
reading
buffer
things
issue.
that weren't written like this cycle.
Yeah,
Right.
exactly.
Okay.
So the yeah, I'm having trouble coming up with a good example here, but the write buffer should be the write buffer should be ahead of the read buffer at all times. You should be writing data to this chunk in memory, and the read buffer should be coming along behind it and consuming data that you've written. And you can assume that anything behind the read buffer is now up for grabs for writing, right?
Right. So yeah, so why not have the write pointer like just one block behind the read pointer?
Dope. I really fumbled the ball on Colin's question here, so I wanted to give a more clear and direct answer about what we're talking about because it's a pretty important point. The write pointer is the position in the buffer where we're going to write our next sample. The read pointer is the position in the buffer where we're going to read our next sample. The write pointer should always be ahead of the read pointer, and only the data between the write pointer and the read pointer is considered valid. Everything else in the buffer is basically up for grabs in terms of it's available to be overwritten by whatever process is writing. Now, in answer to Colin's question about why the pointers aren't always just like right next to each other, I think probably a good example is like a delay effect where we want to delay the signal that's coming in by some number of samples or some number of milliseconds. Um, so imagine that you have this signal coming in and you want that to be delayed. So it comes in, it's in the input buffer. Instead of writing it directly to the output buffer, you would write it off to this circular buffer that you've allocated, when the program started. And so you're writing to that, and then some number of samples later, you're going to start your read pointer is going to come along and start consuming from that buffer. And a lot of times, what you'll do in that case is you'll combine the data that you're taking from your circular buffer. You'll combine that with the data that's currently incoming, that's in the input buffer, and all of this that I'm describing is happening in your audio callback. And then you're combining those two audio streams and putting them into the output buffer. So the output buffer then is a combination of the currently incoming audio with the delayed audio, right? So that's kind of like how a delay effect would work. But the truth is that a lot of effects involve delaying an audio signal by often a very small amount, a sample or two, but a lot of like digital filters will involve looking at the previous sample in the stream, which as we learned about in the audio callback stuff, that previous sample might be from a previous call to the audio callback. So we need to store that somewhere in order to read it. There's also situations like when you have multiple incoming audio streams and you need to synchronize them. That will often involve delaying the audio streams in order to make sure that all of them are playing at the same time. You might need to delay one or more of them so that they're all in sync. But yeah, those are all some uses for circular buffers, and you'll see those quite a bit throughout your journey in audio programming.
Well, so you don't want your read pointer to surpass your write pointer, but you also don't want your write pointer to surpass your read pointer.
Well, yeah, I mean that's a different kind of problem.
Right. So I guess you want them to be like as far apart as possible, probably.
I don't know about as far apart as possible. It's just that you can't read data that hasn't been written, right? If you write data that hasn't been written yet, that's a problem. But if you read data that hasn't been, I don't know if I said that right. If you if you write data that hasn't been read yet, that's a problem. If you read data that hasn't been written yet, that's also a problem. It's the chunk of memory in between the read pointer and the write pointer is what's valid, essentially.
Okay, that makes sense. So I think it makes sense that they're not next to each other, because you probably need some based on performance of something. You need there to be that. I think that makes sense.
Yeah, I would guess they're usually separated by a block of samples, usually. Okay. But I don't know that for sure. But yeah, really good questions. The ring buffer or circular buffer is something you'll see a lot in audio programming. And then just like we were talking about, threads. Any audio application is going to basically be multi-threaded, and that presents its whole. It has its whole own set of issues, right? Especially when you take into account now that your audio application probably has some kind of user interface, and you need to like read information from the user interface and then process that as part of your audio processing callback. You need to like do some coordinating, because your audio callback is being called in its own high priority thread. The UI might even be in its own thread, or it might just be like out there somewhere. But regardless, you need some kind of synchronization between the audio callback thread and the main thread or the GUI thread or whatever it is.
Yeah, that in my mind is very, very easy to imagine how difficult that gets, making sure that everything is in sync.
Yeah, I've even read about these bizarre cases where like stuff will interrupt the audio callback thread in the middle of writing to a specific value, right? So you'll get like, you'll have like a like an 8-bit, or let's say like a 32-bit float, and half of it will be written, and then the thread will interrupt, and like it'll come in, and then like you'll have a float value that was like half written. You know what I mean? It's like you can even have stuff like that. You need to be really careful with, and you need to use like atomics and in general, the framework that you use will give you the capability to like read and write these values without too much trouble.
Okay.
Yeah. So next we're going to look at some code. I think that's enough prep work. We'll look at some code next.
Oh yeah.
1X Developer Podcast.
Hey everybody, this is Colin. First and foremost, I want to thank you all for listening to this episode of the 1X Developer Podcast, and let you know that if you have any questions, comments, or if you just want to tell us about your day, you can reach us at X, formerly known as Twitter, at 1X Developer Podcast. We're also on YouTube at 1X Developer Podcast. You can email us if you're weird at 1xdeveloperpodcast at protonmail.com. And lastly, don't forget to follow, subscribe, all that stuff, so you don't miss any further episodes of the 1X Developer Podcast. Thanks so much. See you next time.